Hello guys, this is Zane here, and today we're going to talk about SUVAT equations and their applications in physics. Firstly, we will ask, what is a SUVAT equation? To answer that question, a SUVAT equation is an equation that describes the motion of an object with constant acceleration, and I will go over why that is so later on. Something that is quite important right now to understand is what each quantity essentially describes. For instance, if you were to write this out as an acronym, each of the letters of SUVAT derives a different quantity. For instance, S stands for displacement, which is a vector by the way. Not to be confused with distance. U is equal to initial velocity. V is equal to final velocity. A is equal to acceleration. And then finally, T is equal to time. If you're having trouble remembering these two, just remember that V comes after U in the alphabet, so it makes logical sense for U to be initial velocity and V to be final velocity. Now that we know these units, we can move on to using them in equations and possibly deriving them. Okay, so deriving SUVAT equations, we're going to do this on a velocity time graph, which many of you are already familiar with, but for those who aren't, you have time displayed on the x-axis here with the units of seconds, velocity on the y-axis with the units meters per second. This is the initial velocity over here. You have final velocity over here. The area under the graph is equal to displacement, if you didn't know already. And then this unit coming from here to here will be time. To begin with, we're going to start with this equation here. V is equal to U plus AT. When we're deriving this one, essentially we're actually trying to solve for acceleration. To solve acceleration in this instance, you can just use change in y over change in x. So as you know, that is equal to y2 minus y1 over x2 minus x1. In this instance, our y2 value is v, and our y1 value over here is u. So v minus u. And our x2 minus x1 is just time over here, because this is change in time. From over here, we can just multiply through by t. So we've got AT is equal to v minus u. And then upon adding u to both sides, you end up with v equals u plus AT. This one is the easiest to derive. And then this is your end point. For our next equation, we're just going to be imagining that this entire area here is equal to a trapezium, and we're just going to work out the area. So as you know, the formula for working out the area of a trapezium is equal to 1/2 multiplied by A plus B, where these are both parallel sides, multiplied by the height. So imagine it in this context, we have this side here, which is u, we have this side over here, which is v, and then t can be thought of as the height. So just using this equation here, we can plug in our values, and of course you know that this is equal to s. So s will therefore be equal to 1/2 multiplied by u plus v multiplied by t. Simply done. Now, for our next derivation, we're going to actually need to split this trapezium-like shape into a triangle and a rectangle. And as you know, since we're trying to work out s, we are of course looking for the area under the graph once again. First of all, we know that this height is equal to u, and then this length here is equal to t. So you can quite easily state that this area underneath here is going to be equal to ut. However, we've already worked out this rectangle here, and now we're going to have to work out this triangle shape over here. So you know that because this height is u and this height is v, this height over here will be v minus u. And then of course the base is equal to t. So you have ut plus 1/2 multiplied by t multiplied by v minus u. Now, to reach our desired form, we're going to have to use another equation to substitute in. So we're going to use the one which we derived earlier, v equals u plus at. But what we're going to do here is we're going to essentially try and get it to v minus u. So if we subtract u from both sides, we get v minus u is equal to at. Now because we've got v minus u over here, we can substitute this in over here. So instead of being 1/2 t multiplied by v minus u, we have 1/2 t multiplied by at. So that gives us s is equal to ut plus 1/2, and then because you've got 2 t multiplied by t, you have t squared, so it's 1/2 a t squared. And then that is, of course, our desired form. On the next equation, as you can notice, this is already very similar to the one that we did before, so it won't take much work in deriving it. First things first, we're going to use v and we're going to use t, multiply them together, and we get a rectangle shape over here, and that is this entire area here. However, seeing as we don't want this area here, we're just going to use the area of the triangle, which we derived earlier, as being 1/2 at squared. So let's start this with s is equal to vt. And then, of course, because we're subtracting this triangle which we made earlier, it's going to be vt minus 1/2 at squared. I'm not going to derive how I got this before, but just view the last derivation if you would like to know why this triangle here and also this triangle here is equal to 1/2 at squared. For our final derivation, which is v squared equals u squared plus 2as, this does not require a graph to be derived, so we have just got two equations here, and then we're going to substitute this one into here and then rearrange it to make that. So first things first, we're going to rearrange this so that we can isolate t, so we can substitute it into here. So if we arrange this, you can get v minus u over a is equal to t. Then substituting this in, you get s is equal to 1/2 v plus u multiplied by v minus u over a. Now to make things simpler, we can multiply by 2a just so that we have only two brackets on this side. So we have 2a s is equal to v plus u v minus u. Now if you notice here, we have v plus u, v minus u in the brackets. If you've done difference of two squares before, so a squared minus b squared, you'll know that this can be placed into brackets like a plus b, a minus b. You can expand this and then you'll get that. So knowing this, you'll just know that 2as is equal to v squared minus u squared. And finally, you can isolate v squared by adding u squared onto both sides, and you end up with v squared is equal to u squared plus 2as. Just as a quick side note, SUVAT equations only work with constant acceleration, because if you imagine that this is not a constant acceleration and you end up with a curve over here, we cannot use the equation that we derived earlier because that relies on this being a triangle-shaped object. Now that we've derived each of the SUVAT equations, we can go ahead and use them in a problem. As you can see from this problem here, problems with SUVAT equations tend to be quite wordy, but it's just a case of finding each quantity and then labeling them underneath. As you can see here, we're calculating the time, so we know that time is going to be involved in one of our equations. Next, you have the displacement here, which is equal to 1.5 meters. And we're also given the acceleration, 9.81. Now, at this point, you will have to apply your own knowledge. So as you can see in this instance, an apple is just fallen from rest, which means its initial velocity will of course be equal to 0. I haven't mentioned this yet, but each equation has 4 quantities in it, so you'll have to just find the equation with each of these in it. And on this occasion, we're going to be using S is equal to ut plus 1/2 at squared. And then at this point, it's just a case of rearranging for t and then placing the values in, or you can place the values in first and then rearrange for t. It's all up to you. I'm going to substitute the values in first and then rearrange for t. First of all, we have 1.5, so I'm just going to place that there. 1.5 is equal to, in this occasion, seeing as we have the initial velocity as 0, this whole expression here becomes 0, which makes it very simple. So then we're just dealing with 1/2 at squared. So we just have 1/2 multiplied by 9.81 multiplied by t squared. So I'm just going to rearrange this and solve for t now. Now I'm just going to multiply each side by 2. So I get 3 is equal to 9.81 multiplied by t squared. Now I'm just going to divide through by 9.81. So I get 3 over 9.81 is equal to t squared. And then it's just a case of square rooting the entire expression. To solve for t. Finally, after using our calculator, we can figure out that t is approximately equal to 0.55. Thank you very much for watching, guys, and that's all for today. If you have any more topics that you'd like to suggest for me to do in the future, just drop a comment. Apart from that, see you next time.